I guess so. So thank you very much for coming today, everyone, both in person and on Zoom. So today we're very lucky to have Professor Tongcang Li from Purdue University to visit us, and he's going to tell us some of his very interesting recent works on optically addressable spin qubits in 2D materials. Tongcang, I think, he's a very good friend of mine, and he received, I think, his PhD from UT Austin, and then did his postdoc at UC Berkeley. After that, he joined the Department of Physics at Purdue University and started his faculty career. So let's welcome Tongcang. Thank you so much.
Thank you for the introduction. So today I'm going to talk about our recent work on optically addressable spin qubits in 2D materials. In the talk, I will first give a brief introduction to spin defect in solids. Then I will talk about our work on, by the way, the spin defect in 2D material was discovered in 2019, which is only about 2 years ago or 3 years ago. So I will give a brief survey on the field, including our own work and some work from colleagues. So I will talk about the high contrast plasmon-enhanced spin defect in HBM, quantum sensing and imaging with spin defect in HBM, and towards nuclear spin control in 2D materials, and our other work, including our proposal time crystal back to 2012, which is about 10 years ago, and has been realized already. And then I work on left optical mechanics and Casimir effect, which is about optical mechanics with virtual photons that do not require high Q cavity. Okay, so there are different kinds of spin defect in solid. One will be quantum dots, and like a silicon carbide, or the most famous one will be the spin defect in diamond. In particular, NV center, which is formed by substitution of carbon atom by a nitrogen atom and a nearby vacancy. And the electron can be trapped in the vacancy. Okay, and this will form a nice energy levels. So for diamond is a very band gap material. You have, valence band and conduction band. The band gap is about 5.6 eV. And then when we have an NV defect, we will create a new energy levels in the band gap. Okay, so we have quantum state, which is spin one system. That means electron spin can be 0 or plus minus 1, and the excited state. Then we can shine a laser to excite from quantum state to excited state, and with decay. And this decay depends on the spin, depends on electron spin. So by shining a green laser, like a 5.532 nanometer laser, we can polarize electron spin to spin 0 state. And we can also read out the electron spin, because spin 0 state is brighter than the plus or minus 1 state. Okay, so this allows us to initialize spin and read out the spin. And if we add a magnetic field, then because of Zeeman effect, the energy level will change. From there, by measuring the electron spin resonance, we know the resonance frequency, so we can measure magnetic field and other things. So there are lots of applications of spin defect in solid. Here I give a particular example with diamond. So people, for example, Michel Lucan's group have demonstrated using spin defect in diamond for memory and to do memory enhanced quantum communication. That work was done just 2 years ago. And in principle, we can also use spin defect in diamond for quantum computing. So this is work done a few years ago, and they used to realize a 10 qubit system with 1 electron spin and then 9 nuclear spins in diamond emission center. There are a lot of work using diamond emission center for quantum sensing and quantum imaging. In fact, this is commercially available right now. You can buy directly scanning diamond NV magnetometer, which can give a resolution about 50 nanometer and can measure magnetic field very sensitively. Here is an example. You use a diamond emission center to map out the magnetic field distribution of a 2D magnet. So you can distinguish, for example, monolayer will be ferromagnet, 2-layer anti-ferromagnet. and you can identify the magnetic property layer by layer. So there are many applications with diamond emissiveness. But of course, it also has drawbacks. One drawback is, diamond is a 3D crystal, and if you cut the diamond, then the surface will have dangling bonds. All kind of different material can be absorbed on the surface. You can have hydrogen or OH, oxygen, and so on. And those can cause noise, like charge fluctuations and other things. So the property of diamond emission will decrease when it's close to the surface. Another thing is diamond is a very good thermal conductor. In some sense, not good for measuring temperature. For example, if I use a nano diamond to measure the temperature sample, then the contact is pretty poor. But if you use bulk diamond to measure the temperature sample, because diamond works as a bigger heat reservoir and cannot respond to the temperature change easily. Okay, so if you want to avoid this kind of problems, you would like to have spin cubes in a 2D material. Then the 2D material will be very thin, so have little thermal reservoir, and also can have very good contact to the sample. Another one is for magnetic field sensing. Diamond emission can allow you to have pretty good sensitivity of magnetic field, and with a resolution from tens of nanometers typically. But if we use 2D material, you can put a monolayer 2D material on top of the material you are interested in. So in principle, you may be able to reduce this separation to be 1 angstrom. So there's a chance towards angstrom scale magnetic field sensing. Okay. So there are a lot of interest, and people have been searching this spin cubes in 2D material for a long time. And it was eventually discovered in 2019. It turned out that the boron vacancy in hexagonal boron nitride is a spin 1 system. And not only spin 1, it's also optically addressable spin 1 system, which means it will be similar to diamond emission. You can use a laser beam to polarize it and then read out the spin state. Okay, boron vacancy basically a missing boron atom in the lattice, and the electron can be trapped in the vacancy. Here shows the optically detected magnetic resonance of boron vacancy in 2 different magnetic fields, 0 millitesla and 10 millitesla. So you can see it's very different. That means you can also use this one to measure the magnetic field. This one is room temperature, 300 Kelvin. So there are several advantages with the boron vacancy in 2D material. In hexagon boron, it's very easy for integration because of van der Waals material. So you can just peel it off and then put it where you want. And also have transit towards angstrom scale quantum sensing. And also very importantly, works over very large temperature range from 0 Kelvin to 600 Kelvin. But also have some drawback, this one particular. One is you can look at this one carefully. The contrast is about, let's say, 0.5%. So the ODMR contrast was low before our work. And also pretty dark. Is not as bright as diamond emission. So we would like to basically solve these problems. And this, as I mentioned, was discovered in 2019. So now I'm going to talk about our work. Before this was discovered, we have been working on like a color centers in boron nitride at that time. For example, here's our paper in 2018, talk about single photon emission from boron nitride nanotube. We have found that we can have some defect on the nanotube, and there will be a quite good single photon emitter. And we can use another laser to modulate the single photon emission. Okay, so the other time we also thinking about the spin defect. Once we read their paper, we feel this is quite interesting. We want to go ahead with the spin defect. So this single photon emitter in boron nitride nanotube is a single photon source, so it's single. But for the vacancy in 2D material, is an ensemble.
I see. So this is not boron vacancy.
This is not.
It's some different.
This one ensemble.
I see.
This one single. I'm just saying we have been working on this at their times. That's why when we saw their paper, we directly jump in to work on this. So now, if we want to work on this, the first thing is we know quasar boron vacancy defects. Okay. So the older work when they publish this paper, they use a neutron source to radiate the boron. So the neutron can be captured by boron and cause a nuclear reaction, nuclear change. And so they are quite difficult. We don't have the neutron source. So first we try the femtosecond laser lighting with a spin defect. Maybe I need to move this somewhere. So we first use a femtosecond laser lighting. So we just use a 800 nanometer femtosecond laser and pass the HVM flick, and there we create like vacancies. We found that we can create this spin defect, and then with quite good contrast, reasonable contrast. Yeah.
So after later writing, it will just naturally become a charge defect, or you apply some gating to transfer from the neutral defect to the charge defect.
So what we believe is when we use a femtosecond lighting, we will create both negative charge and the neutral one. We didn't do any extra control. Okay.
What happens if we use a different wavelengths?
You mean this one?
Yeah.
This wavelength? They may have some effect, but I don't think it will have dramatic effects.
We'll create both with boron, the nitrogen vacancy, or just create.
So, I mean, in this paper, we mentioned that, in fact, it really depends on the laser power, peak power. Okay, if the peak power is not correct range, we create a low defect but don't have this ODMR. So we need to choose the correct energy range. Okay. One possibility is, for example, if the energy too high, it may like create a, not just single vacancies, but like clusters of this defect, and then they are not good for this ODMR measurement.
So using the femtosecond
So this one, no really. So that's why we want to move forward. We can control the density by number of passes, okay, but not they are accurate. By increasing, okay, the peak power is crucial to create this kind of defect. But once you fix the peak power each single pass, then the more pass you put, the more vacuum you create.
So still it depends on the resolution.
Right. So this we can create a cloud defect with spatial resolution under 1 micron. So we want to go beyond that one, and then
now you want to talk about single layer.
so now we want to reduce the thickness. So then we want to create a spin defect in HBM with ion implantation. So we built a small ion implanter, and we turned out the healing ion is the best to create this defect. And we did some calculation. So the depth depends on energy. So with, for example, 300 volts, the average depth will be about 3 nanometer. And you will increase the energy to 3 kilo eV, then the average depth will be about 30 nanometer. So with that, we can create a homogeneous spin defect across the surface. But depth can be controlled by the energy, or we can peel it off later to reduce the depth. Okay.
So in this case, it's not like a focus IND. So you don't
Right.
focus the IND.
We don't
you already
focus.
get a whole.
So our own ion implanter can irradiate the flake with a size up to about 1 centimeter. So it's pretty homogeneous. Okay. And of course, if you want to create locally, one way is you use, for example, like some mask, like a photorest and each other with some holes. Then we can implant the host with these ions. Okay.
So you use the 5 micron.
This one,
Yeah.
this is just one example. We show it's quite homogeneous, but we also have larger samples.
We use them.
This one, no. We just directly put the flake on silicon wafer.
And the very resolution is on 1 micron.
You mean this one? In this case, we eliminate homogeneously, so there's no resolution. the whole flag will be will have a spin defect homogeneously.
And the size of the sample is bigger than the.
Yeah, but that will be like a millimeter or centimeter scale. Our flag is not that big. Our flag typically on the order of 10 micrometer to 100 micrometer maximum. Within that range, we can choose as a homogeneous. Okay. And then, so now with this spin defect, great. We want to enhance the brightness. One way to do is use plasmonic enhancement. Because we also want to use this one for sensing. So we want to use the simpler geometry possible. The simpler, the better. So the simple one is directly put the HBM flag on gold film. Okay. And if you look at gold film, use AFM, you can see it's smooth, but not perfect smooth. Can have a roughness on total, peak to the measure every roughness is like only 1 or 2 nanometer. But you look at peak to peak, can be about 10 nanometer. And this is enough to support the localized plasmas. So there's work, for example, done before by the hard spot. The hard spot by surface roughness is naturally has size on total like a 20 to 50 nanometer, right? So 50 nanometer scale, hard spot. So with this hard spot, you can choose a tiny optical cavity with a size on total 50 nanometer. So that can give you pretty good per cell enhancement to increase the brightness. So we try to study plasmonic enhancement. We compare 2 different cases, HBM on sapphire, which have no plasmonic enhancement, and HBM on gold film on top of sapphire wafer. And we can see the HBM on gold film is about 15 times brighter than the HBM on sapphire. And we also want to see, remember this guy have some size, plasmon size scale on total 15 nanometer. So to prove this is really due to hard spot, we also change the thickness. So only the top layer, top few nanometer has spin defect. And then we can control the thickness. So that means we control the separation from the spin defect to the gold surface. Okay. By changing the separation, we can see the enhancement reach the peak when the thickness is about 40 nanometer, and then decrease very fast, means thicker. So that shows this is really due to plasmonic enhancement instead of just reflection.
Why is this top maximum is
This one?
Yeah.
The widths are more or less the same thing, but this one is smaller, so we cannot see. A little broader, not too much. Okay.
How do you, so you're generating these defects again with that broad ion beam?
Right. So we first generate the defect with broader ambient, and then we transfer this HBM flag to gold.
So how do you know that the defects are only on the surface and that there's not any?
Oh, so that's one we basically control the energy. We use low energy ion implantation, so the ions cannot go deep.
Yeah.
Okay. And then we use AFM to measure the thickness. So the thickness, in reality, we don't control the thickness. We just put the figure there and then use AFM to measure the thickness. Okay.
I have a very question about this plasmonic enhancement. So it only enhances, is my understanding correct? Like it only enhances the laser excitation?
No, do both. Laser excitation, that is you think like a lens to focus light a little bit.
Yeah.
But more important is not that. More important is the per cell effect, which is basically you increase the quantum vacuum fraction there. So you speed up the decay.
Oh, I see. So you indeed see like the lifetime of the defects.
Right.
Much shorter. I see.
A little bit short for this guy. But in general, if you put a time emission there, the lifetime or quantum dot, the lifetime will be much shorter.
I see.
But in this particular material, the decay is dominated by non-radial decay. So you see a change of the lifetime, but not dramatic.
I see.
Okay. Yeah. So the main effect is use cavity plasmonic enhance quantum vacuum fluctuations. So that's you will spare the spontaneous decay. And then we also studied different materials. For example, we compare sapphire I mean, silver gold and then silver, silver, ITO, silicon oxide. And those silicon dioxide or ITO and silver do not have plasmon enhanced. Only silver and gold have. Okay. That's also confirmed this plasmon. And then the plasmon speak about the spin polarizing a little bit, not too much. And we compare silver and gold, speak about somewhat maybe by factor 1.5 or so. But the main problem is because for this one, the optical decay is just a small percentage of the overall decay. That's why it's very dark. Okay. And then we want to detect the ODMR. Initially, as I mentioned before our work, people only observe like a 1% contrast or even less. Okay. And we found out that the main problem of that, why is it so low, is the direction. Because for HBM, people initially work on diamond emission, and for emission, the direction of spin is random, can be any direction. But for HBM, the spin is pointing out of the surface, okay? Pointing out the surface, perpendicular surface. In this case, you will use a loop. That will also generate magnetic field perpendicular surface. Then this will not drive transition. So we needed the AC magnetic field to be perpendicular to the spin. So that will cause mixing of spin 0 and 1, cause transition. With this one, and this is fabric device. Here is a gold on sapphire wafer. This HBM will be just tiny at the center. Okay, so we have good waveguide. With the other, we have also ODMR contrast as high as 46% at the room temperature. Remember the limit is 50%. Even if you drive it completely, let's say 0 is fully bright, 1 is complete dark. So 1 and 0. And by driving them, you mix half-half. So the maximum contrast you can get is 50%. So we got 46%. That also means the electron spin is nearly fully polarized, more than 90%. And also, we got measure ODMR as a function magnetic field.
Does that mean like actually this defect, like the dark state is just perfectly dark?
Should be very dark. Yeah.
I see.
Yeah, I guess this guy is pretty weak, so the dark state is even weaker.
I see.
Okay, so this is even higher than diamond emission than the contrast as a room temperature. So we also did a test. It is a different like omega shift waveguide, which people typically use for diamond emission. And we drive with even higher power, we get a few percent, but much weaker than 46% we observe. So okay, so we talk about the plasmon-enhanced HBM. Now we're going to talk about quantum sensing and imaging. This I will introduce some college work, including our work about other college work too. So this is a paper published in near the end of 2021, using spin defect in HBM as a promising temperature, pressure, and magnetic field quantum sensing. This is from Vladimir Diakonov's group. So they show, of course, when you change the temperature, the lattice constant will change. So that will change the frequency. And when you add the magnetic field, you will also change the separation, right? So when you change C temperature, 0 Kelvin to room temperature, the center shift to smaller frequency when the temperature increase. So they measure that. By the way, their sample is a bulk sample. They use a 10x aperture lens. So with a millimeter spot of 10 micron. So their sample, they basically collect the signal from a lot of spin defect with a resolution of 10 micrometer. And in their case, they choose magnetic sensing of 85 microtesla per square hertz, which is quite worse compared to diamond emission. And then also temperature resolution of 3 Kelvin per square hertz, and so on. And then we want to use our plasmon enhancement to improve this one. So with the plasmon enhancement, we increase the contrast, but also there's also a trade-off. When we increase the contrast too much, the line is broad. Okay, so the line will increase. Contrast also increase. So there's an optimal situation. When we put the power, let's say scale loss of power is about 0.5 watts. We can improve the sensitivity to about 8 microtesla per kilohertz. But one thing I need to mention, in the older work, they have laser spots 10 micron. In our case, we use 100x to focus to diffraction limit. So the spatial resolution also improved from 10 micron to about 500 nanometer. Okay? So we improved the spatial resolution by factor 20 and magnetic field resolution by factor 10. So that's our work. And then after we use this plasmon-enhanced, now a lot of groups use the same scheme. So there's, okay, we can also measure the coherent controlled spin. So here's a rapid oscillation. You control microwave power, we can change the coherent oscillation of the spin. This is used for people who don't know the purpose. This you can apply like a quantum NOT gate. You apply, for example, pivot 2 pass. You can flip from spin 0 to spin 1. So you can do NOT gate. And we also measure the T1 to be about 17 microsecond. And we measure T2 to be about 1 microsecond. But there are also some debates right now. Some people also produce different results, and this is still undergoing. Okay, and then recently there's an archive paper posted on archive from Songhui Du's group in December 2021. So they now also put HBM on gold waveguide, and then basically use the same scheme as we did. But in addition to HBM, they put a 2D mechanical material, FGT, right? Iron germanium telluride. So then they want to study, use this as a quantum sensor to image the system. So you can see this scale bar is 5 micrometer. So when they change the temperature, when temperature low is a 2D mechanism, ferromechanism. And when you increase the temperature, become paramagnetic eventually. But during the transition, they can see the structure and then also observe spin fluctuations. Okay. They also see a spin fluctuation and the decoherence, the change of the T1 of the electron spin by the spin fluctuation. So this is uses HBM for quantum imaging of 2D magnetic materials. And there's another work. They also use HBM for temperature sensing besides magnetic field sensing. So they can measure the temperature. So basically they have flake and they use a laser to heat up some magnetic material. Then the temperature will change. So what's remarkable is they can control the width of the pulse of the laser. So with that they should see spin dividing HBM can measure the temperature change within 100 nanoseconds. So it's very fast, have very fast time response. Okay, you cannot do this with diamond emission. I mean, because very thin.
Because you mean because of the thermal conductivity?
Yeah, first of all, the material is very thin. Don't have little thermal buffer.
I see.
The capacity is tiny. So it basically changes the temperature immediately. Okay, so that's for this quantum sensing and imaging with spin defect. We are also very interested in to control nuclear spin in 2D materials. I mean, there have been lots of work regarding electron spin in 2D material. You can have magnetic material, right? And then you have top-row insulator where you have spin orbital coupling, and there, and things like a spin liquid and those kind of things. So there are a lot of work with electron spin, but basically little or even no work on nuclear spin in 2D materials. So we would like to start a nuclear spin, which can become an important quantum resource, which people have not worked before. So HBM have, of course, consider boron and nitrogen, and both of all elements, stable elements of boron and nitrogen have nuclear spin. For nitrogen, dominant one is nitrogen 14, which is spin 1. Is a natural abundance of 99.6%. So we mainly focus on this one. But you can also have spin half, spin 3, and spin 3.5. Okay. So if we can control nuclear spin, there are a lot of things you can do. For example, here the theoretical proposal, probably in Nature Physics a few years, 9 years ago, they proposed If you have a nuclear spin lattice, then you may be able to do larger scale quantum simulation. With a nuclear spin lattice, you can also use a change orientation magnetic field to control the interaction between them, or use a microwave RF. Even though the separator is fixed, but you can actually change the nuclear spin interaction between them by either tuning magnetic field or RF. So you can tune them to do quantum simulation to start different phase of them. So if you want to control nuclear spin, first of course, the energy level is quite complex. You need to understand them. So this is like a calculation done by our collaborator, Professor Yang Ping. So the ground state have of course ground spin zero field splitting about 3.5 gigahertz. Then the excited state means the excited still goes first go to 3E double prime state and then go through a very fast very relaxation to go to 3A2 state excited state. So again, this field is very new, so people don't know the parameters. Before our work, people don't know what this DE is, okay, and the other parameters. So first of all, Professor Yang Ping's group did calculated the spin density of the ground state. Ground state is symmetric, rotational symmetry. The 3H state symmetry, but excited state is not a symmetry breaking, reduced to C2V symmetry. Okay, that also will affect the nuclear spin polarization. So now, if we really want to polarize nuclear spin, now remember, this is far more complex than diamond emission. We have so many nuclear spins surrounding the line, nuclear spin bus, all atoms have nuclear spin. And the dominant one will be neighbor 3. And these neighbor 3 are identical. Okay, so you cannot really distinguish them, all the same. So we you can think of the spin 3 system, not really spin 3, but the 3 nuclear spin have 27 states now. And if you classify them by the sum of the G components of the nuclear spin, then you have 7 components, +3 to -3. And then we will use green laser to excite it, go excited, and if, for example, you have level anti-closing, if we bring this excited spin 0 and -1 have the same energy, then they can mix. Okay, the electron spin and nuclear spin can flip-flop, so they can couple, and by this cycling, there's chance. So if you look at, for example, initial -3 state go up, -3 and mix becomes -2. Okay, decay back. So after a few cycles, in principle, you can polarize to +3 nuclear spin state, ideally. But to do that, first of all, we need to make this energy like a degenerate. So to do that, we need to know DES basically. So recently, we collaborate with Professor Fuchs in Cornell University, and they use our sample to perform this measurement. So they also put the HBM on plasmonic waveguide and then measure. So this was done at low temperature. So in addition to ground state electron spin regions of 3.5 gigahertz, we also observed the electron spin regions at 2.1 gigahertz, around 2.1 gigahertz, and that's due to excited state. And then we measure this spin energy levels as a function of magnetic field. So you can see the excited state have level anti-closing at 750 Gauss, and ground state have a level anti-closing of 1,200 Gauss. So now we know this excited state spin is 2.1 gigahertz. So in principle, we can go to these levels to perform nuclear spin polarization. We are working on that. These are all, I mean, these are have not even published. So we still are working on this nuclear spin polarization.
And is this excited state zero field splitting actually matches with the simulation or the modeling?
So pretty close, not exactly, but pretty close. Yeah. So in order to confirm this really excited state, we also perform the laser excitation. One is CW laser excitation, where you observe both ground state and excited state. The other use a pulse one. You basically you use laser to initialize and then turn off the laser. Once you turn off the laser, the electron will decay from excited state to ground state. So there will be no more excited state. And that's why we only observe one peak in ground state and no peak to the excited state. So that confirms this is really excited state. So yeah, so with this one, now we are working on nuclear spin polarization. So we still have some time, and then I'm going to talk about my other works, okay, briefly. My work on time crystal, level of intense, and virtual photons. Time crystal very briefly. So in 2012, we published a paper of space time crystal ions as a cover PL, together with Professor Frank Wilczyk's paper on quantum time crystals in the same issue of PL. At that time, we published we caused a lot of debate, and then people now also improved these concepts and then develop new schemes. And eventually, it has been preserved now. So now the discrete time crystal has been preserved with both diamond in centers, electron spin, and also so this is with diamond in center. And the other is with trapped ions. So they published as a cover Nature a few years ago. And recently, Google also used their quantum computer to create a discrete time crystal. And then, but I'm mainly working on other work. Remember, our spin defect happened 2 years ago. So before that, my focus was on optical levitation. So for that, we can use a laser beam to levitate the nanoparticle. This was pioneered by Arthur Ashton, who received the Nobel Prize in 2018. So in our experiment, we can shine a laser beam from the top down up, and then you shake the glass bead, the glass bead will fall off and will be supported by the light. Okay, so this bright spot here, it does not touch anything except the light. So it was fully supported by light, right? The radiation pressure from the light.
And this is a vacuum, or is it?
These particular pictures in here, but we can also do the same thing in vacuum.
I see. In air, so it's just in atmosphere. Okay.
Yeah,
I see.
in atmosphere. And then the purpose of this, there are many things to do. I'm just focused on one thing. That's my work at Purdue. So basically, we want to create a so-called optical limited cavendish torsion balance for quantum limited torque and force sensing. So the original cavendish torsion balance formed by two balls suspended by a wire, right? And if you have a torque, the orientation will change. And this was done more than 200 years ago. I measured torque, a remarkable torque as small as 10 to the minus 7 Newton meter due to gravitational interaction more than 200 years ago. And this work determined the gravitational constant G. In our experiment, we want to reduce the size. We want to shrink down the cavendish torsion balance from 2 meters to, let's say, 200 nanometer. Reduce size by 7 orders. With that, we can improve the torque sensitivity by 20 orders to 10 to the minus 28 Newton meter per gigahertz. So to do that, we need to make these nano dumbbells, and we create a biochemical synthesis. So we can create a silicon nano dumbbells, and if we use if the laser is circularly polarized, the laser will the angular momentum, the spin angular momentum photon will drive the nanoparticle to rotate. And this work is done in vacuum. So little air dissipation, that means it can rotate really, really fast. So we drive the particle to rotate beyond the 60 billion revolutions per minute in 2018. So this is basically the world's fastest nanorotor. In fact, it's more than 100,000 times faster than the high-speed dental job. So I'm very glad that our work was selected as a top 10 highlight of the year of 2018 by APS Physics. So remember, our initial motivation to detect small torque, right? So why is it very cool to try to rotate very fast? But we want to see whether we can really detect a small torque. So to do that, we add another laser. So the pink laser or infrared laser is for trapping and detection. And then we intentionally add another laser to give a small torque. So we can see whether we can measure it. And when we modulate the power of the laser sinusoidally, the rotation speed will also change as a function of time. And with that, by taking data for 100 seconds, we can measure torque as small as 5 times 10 to the minus 28 Newton meter in 100 seconds. So this is the what is most sensitive torque detector right now. So I worked with in Nature Nanotechnology about 2 years ago. So that's for left optical mechanics. And my last topic is quantum optical mechanics with virtual photons or Casimir effect. So people have been working on quantum optical mechanics to use a cavity to enhance the interaction between photon and a mechanical resonator. You need a very high cavity. So the cavity will confine the photon to bounce back and forward many times to enhance the interaction. And people, for example, can use this photon in the cavity to cover 2 mechanical resonators. Right? So to do that, you need a lot of photons to cover them. So the coupling is quite weak. Large number of photons is required to achieve coupling. And the quality factor of the cavity should be high. And this becomes very challenging. You want to put two membranes inside. If you just have cavity, you can line. Put one membrane, then it becomes more difficult to line because if the membrane is misaligned, you reduce the quality factor. And put 2 membranes, become more complex. So instead of using large number of photons, we propose use virtual photon, 0 photon. So what you do is this. In reality, quantum electrodynamics predicts there are lots of quantum vacuum fluctuations in vacuum. So there are low virtual photons. Okay? The virtual photon is 0 photon for each mode, but there are lots of modes. Every given frequency will be an electromagnetic mode and have a 0 photon state, which have energy. And then you will put, for example, 2 mechanical resonators very close. Then this quantum vacuum fluctuation effect can be very large. Okay, even though it's 0 photon, but there are so many modes. The effect can be big, and then we don't even need a high Q cavity. So here's the experiment setup, and we built a basically dual cantilever AFM system. We have 2 fiber interferometers to monitor their motion independently. So first we measure the Casimir force. So you can see this force basically proportional to pi to the 3 h bar c over 120 and times 1 over x to the 4th power. X is the separation. So this Casimir force only depends on speed of light and the Planck constant. So this is a pure quantum force due to quantum vacuum fluctuations. Okay, so we measure that, and then when we module them to match the frequency, we can also observe strong coupling with virtual photons. And recently, we also demonstrated we call the Casimir diode or non-reciprocal energy transfer. Basically, we have 2 coupled optical resonators, and we can control 2 parameters. One is the modulation frequency. Oh, by the way, initially these 2 resonators have different frequency. One is omega 1, the other omega 2. So they do not really couple. And then we modulate the separation equal to, let's say, omega 2 minus omega 1. So we have parametric modulation. And then we can cause coupling. Okay? The parametric modulation is possible here because this Casimir effect is highly nonlinear, depending on 1 to the x to the 4th. So when you move the separation, the gradient also change. So by changing the frequency and the amplitude, we have 2 parameter control, and we can engineer an external point in the structure space. Okay, and then the simplified interaction Hamiltonian can be like this. So we have an external point, and of course, Professor Lanyan did a lot of work in this external point. We are just beginners in this field. So, but this is the first time people choose the external point with the quantum vacuum fluctuations. And then we can modulate data along a loop, and we can demonstrate energy transfer in 1 direction. So for example, clockwise loop, energy transfer from 1 to 2, and then cannot go from 2 to 1 blocked. So work like a diode. And when we change the parameter in anti-clockwise, then we can have energy from 2 to 1, but not 1 to 2. So we call the Casimir diode. And paper was just come out very recently in Nature Nanotechnology. So this is 2 cantilevers. And now we go one step further to study 3-body Casimir effect. So now we have put 3 cantilevers. We put 3 optical fiber interferometers. There's another one I didn't show here. They're basically 3 fiber interferometers to monitor the motion of 3 cantilevers. And we also, so this is the first time people measure Casimir effect between 3 separate objects. So we can change the position of the needle. And we can see the force will, when it's closer to the left one, will be attracted to the left one. And when it's closer to the right one, will be attracted to the right side. In middle, the total Casimir force is only 0. And we can also change the left side and the right side. And with that, we also try to demonstrate similar like a kind of like a Casimir transistor. So we have a 3-terminal device coupled by quantum vacuum fluctuations. So we have energy, can drive one cantilever and see whether we can couple this energy from left to right. And then the center one is the gate. Okay, similar like a field effect transistor. We apply gate here. You can turn on the off. Basically, you don't modulate it. Then there will be no coupling because their frequencies are all different. Okay. When you modulate, they can couple. And even more, we can add a gain to this one. How we add a gain to the mechanical resonance? Basically, the feedback. So we monitor, we have fiber interference monitor motion, and we feedback this signal to the piezo. So to add a gain to this one. So with that, we can achieve switching and amplifying the 3-body Casimir effect. So I think I will stop here. So this work, and I'd like to thank my students and collaborators for funding.
Thank you so much, Tongcang, for the amazing talk and all different amazing directions, so many directions. So I think we have been already discussed a lot of questions. So if there are more questions, feel free to ask.
I think you will.
I was just wondering if you can make a Casimir parametric amplifier.
Yeah, that's something we are very interested in right now. We are designing that parametric amplifier. Yeah, we are thinking to make a. Right now, we started fundamental of Casimir, but we want to have new applications. So the Casimir parametric amplifier may allow us to amplify signals. So we are designing right now. Yeah.
What's the drawback of using boron?
Right now, the main drawback is pretty dark. Does not emit as many photons as a diamond emission. Okay, maybe easier to go to here. Energy level. So there are many energy levels. For example, here I have value relaxation go here, but this state, it does not. The chance this guy go to here. Non-radial decay is like thousands or 10,000 times larger than this radial decay. So basically, the state decay or give us energy by maybe photon or heat instead of photons. So there are also people working on how to engineer this one to be better. Right. Yeah.
Is it? I mean, I wonder if you need to scale up. We focus on the small size of the image, right? Do we need to scale up?
Yeah, maybe some application will require that, but for our research, we don't need a big one. But in future, for some engineering applications, it's possible. You may want a wafer scale. By the way, you can buy HBM on wafer scale. They sell even monolayer boron nitride with a diameter of 4 inches. So we just didn't use it.
Why I'm wondering is that for them, the electronic side, if we focus on the single device, but still we cannot make like some circuit level demonstration. Is there anything like that?
Can I repeat again?
For example, the electronic side, if we still focus on the transistor, transistor cannot work at the circuit level demonstration.
So HBM is an insulator. So maybe it can be used as a gate barrier, but cannot really use them for the active part of the device. It's a wide bandgap insulator, similar like a silicon dioxide. So there are people, or even right now, even there's a work they use HBM as a barrier to create a superconductor qubit. So they use HBM very thin and then put a two superconductors separated by HBM. So that one you can create a superconducting qubit. So there are many applications right now. Yeah. Any other question?
Yeah, I have a question about experimental configuration for the last experiment, the catchment effect.
Right.
So the probe, there's a microsphere attached to the probe. So what is that?
Okay.
Yeah.
So if you just think about the mechanical resonator, you do not need a microsphere. The reason why we put a microsphere, we want to make this equation simple. So the microsphere, when you have a sphere in the surface, you don't care about the orientation alignment.
Okay.
If you have two plates, then the plate can be parallel or tilted.
Oh yeah. Okay.
The plate can be tilted,
got
then I do not have this nice feeling anymore.
Yeah.
But with a sphere, when you have a plate and sphere, the only parameter is separation. So basically, we want to compare with the feeling.
That's creative. Thanks a lot.
Right. So that's why we intentionally even
Got
put a two, so we can compare with feeling. Otherwise, there's no way
Yeah.
to compare with feeling.
Exactly. That's creative. Thanks.
Right. Yeah, if they do not grade, people will not charge us. We have measured cascade effect.
Oh yeah.
So why not use two spur?
Oh,
Use spring.
yes, but then the alignment becomes even more difficult, right? Plate and sphere is easier. Two sphere, then you need to align the relative position. If it's like this, it won't work. But plate, you don't care, as long as within the range.
Yeah.
So yeah, mainly for the to make it explain easier.
Got it.
Okay.
Any more questions? If not, let's thank Tongcang again for the amazing.
Thank you.